The other lesson in Chapter 12 is 12.3, Geometric Sequences and Series. The definition of a geometric sequence is when you multiply by the same value to get consecutive terms. Arithmetic is when you add or subtract. If you have a pattern like 1, 5, 25, and 125, that would be a finite geometric sequence. You know the start and end value. Down below it, 1, 5, 25, 125, ... that means you have an infinite geometric sequence. On the right-hand side, the common ratio is going to now be known as R, and we'll use R in our formulas. That's simply the number that you multiply by. The unique thing about geometric sequences is that our common ratio between terms is always going to be a multiplication rule. We're not going to technically use division rule. Here's what I mean by that. In this first example, we have 3, 15, 75, 375. What we're doing from one term to the next is multiplying by 5. So that just simply means R would equal 5 when we generate our formulas down below. But in the next one, 100, 10, 1, and 1/10, notice those values are getting smaller. Instead of saying that we're dividing by 10 each time, we're going to multiply by the reciprocal of that, which is technically, whoops, I'm saying too many words, technically by 1/10. If we took 100 times 1/10, we'd get 10. 10 times 1/10, we'd get 1, and so on. This means our R value, what we're multiplying by, is just a fraction. Like arithmetic definitions, we're going to have both a recursive and an explicit form. For the recursive geometric definition, we determine our first term a sub 1 for all values of n equaling 1. To get consecutive terms in that sequence, we're going to take the previous term and simply multiply it by the R value. So we could kind of describe this as previous term times the R. Whoops, wow, I keep doing that. Times the R. There we go. And that would get you the next term in that sequence. Over to the right, let's look at the explicit formula. This is the one we'll use more often. The explicit geometric definition just has those two parts, a sub 1 times R to the n minus 1 power. The unique thing about this definition is that it's an exponential equation. And anytime we work with exponential functions, we're going to have to be careful in our process. Let's take a look at some examples. Question 1. Determine if the sequence is arithmetic, geometric, or neither. Explain how you'd know. Example A, 2, 4, 8, 16. What are we doing from the first term to the second term to the third term? Well, I noticed that in the first term I could add 2, but then in the second term I'm adding 4. That means I'm not adding the same thing each time, making it not arithmetic. I could multiply 2 by 2 to get 4, and I could multiply 4 by 2 to get 8, and I could multiply 8 by 2 to get 16. If we're multiplying by 2 each time, that means this pattern is geometric. You try the next one. Pause the video, see if you can determine how you know it's arithmetic, geometric, or neither. Then press play and we'll move on. Did you come up with arithmetic because we're simply adding 2 each time? If you did, that is correct. Very good. The next pattern is kind of tricky. It looks familiar. Let's see what we can do. 1, 4, 9, 16. What do you notice about those numbers? Hopefully you recognize they're all perfect squares. But if we look at how to kind of go from one term to the next, first we add 3, then we add 5, then we add 7. So it's not arithmetic because we're not adding the same thing each time. To multiply, all we can do is multiply 1 times 4 to get 4, but 4 times a fraction would have to give us 9. So it's not geometric either. This is a pattern, but it's an example that is neither arithmetic or geometric. All right, last one. 99, 33, 11, 11 thirds. To go from 99 to 33, if you think about the definition dividing by 3, that's a true description of the pattern. But in order for us to be arithmetic or geometric, especially geometric, remember we use a multiply rule instead of divide. Instead of saying divide by 3 to go from 99 to 33, What if we say multiply by 1/3? 99 times 1/3 would be 33. 33 times 1/3 would be 11, and so on. The same product gets you from one term to the next. Therefore, this is a geometric sequence. And just a little refresher, all 4 of these are examples of infinite sequences. All right, let's move on. Our next example, write the explicit definition for the geometric sequence 6, 18, 54, 162, and so on. It says verify the first 4 terms. I think we'll just look at the first 2. But first, let's write our explicit definition. The template that we're going to use is the template up above. The nice thing about geometric, kind of in this part of the lesson for today, is that the template is super easy to work with. There's nothing to simplify once you plug in what you know. A sub n equals a sub 1 times r to the n minus 1 power. All we need to determine is a sub 1 and r. A sub 1 is the first term in that sequence, and that's 6. R is what we multiply by to go from term to term. From 6 to 18, we'd multiply by 3. 18 to 54, we'd still multiply by 3. This makes our common ratio equal to positive 3. Our formula then, we're almost done, is just a sub n equals 6 times 3 to the n minus 1 power. But anytime we have this exponential formula, we have to be careful. Remember, we're not going to multiply the 6 and the 3 to get 18. Order of operations, this part would kind of be by itself with that exponent. All right, so let's kind of see how that works with verifying the first 2 terms. It says 4. Let's cross off 4. We'll do 2. That should be enough. To verify the first 2 terms, the first thing I want to do is just define a sub 1 and a sub 2. A sub 1. If I plug in 1 for n on the right, we have 6 times 3 to the 1 minus 1 power, which would be 6, which would be 6 to the 3, or 6 times 3 to the 0 power. Well, anything, remember, to the 0 power is 1, and 6 times 1 would equal 6. And that is, in fact, the first term in our geometric sequence. To get a sub 2, we plug in 2 for n. 6 times 3 to the 2 minus 1 power. Well, 2 minus 1 is 1. 6 times 3 to the first, which would be 6 times 3, is 18. So we're using that formula to verify the first 2 terms in our sequence. When working with the recursive definition, like arithmetic, we're going to use that 2-part template. So over here, I'm just going to kind of define how we'll set this up, and then we plug in what we know. It's a sub n equals, and we do that 2-row kind of rule. We define a sub 1, which is the given number for us, and then comma n equals 1. That just tells us it's the first term. And then we take r times a sub n minus 1, and that works for all values greater than 1. We're literally just going to substitute in a sub 1 and r like we did in question 2. All right, so we know a sub 1 was 6, and we knew r was 3 from that example up above. To write out our recursive version of this, a sub n equals, we do a sub 1, so 6, and then we just write comma, n equals 1, defining our first term. And in that second row, we do r, which is 3, times a sub n minus 1. Remember, that just means previous term. And that rule holds true for anything greater than 1. That's really all you do. You take the first term, multiply it by 3 to get the consecutive terms after. And that's the recursive definition. And we come to a question like number 4. Is the sequence 12, 9.6, 7.68, 6.144, and so on a geometric sequence? If so, write the recursive definition. This one isn't quite as easy as the ones up above to determine whether or not it's geometric. So if the numbers kind of get bigger or smaller, but you're not quite sure by what value, by what ratio, what we do to determine r is we take 2 consecutive terms in the sequence and we divide them. But we have to be particular. We take the second term divided by the first term. So kind of the second term divided by the previous term, and that should tell us what we're dividing by. With these decimals, it might get a little tricky. 9.6 is the second term. 12 is the first term. If I move the decimal over 1 in the numerator, I could make that 96, but then 12 I'd have to move over as well and make that 120. 96 over 120 reduces all the way down to 4/5. If I take 12 times 4/5, I would get a 9.6. To verify that this is true, we're going to do that again. So I'm going to take another round. Now I'll take the third term and divide it by the second term. I know we're dealing with these crazy decimals, but our goal is to validate whether or not the common ratio is the same. Because if it isn't, then we just say no, and then we're done with the problem. The third term is 7.68, and that second term was 9.6. Now I need to move the decimal over 2 places in the numerator, 768, and if I move it over 2 in the denominator, that becomes 960. And through the magic of this video lesson, I know that this reduces down to 4/5 again. This means that the ratio stays the same between the terms, so yes, it is geometric. And our R value is 4/5. It says, if so, write the recursive definition. We know the recursive template. We just wrote it out up above. So let's write A sub n equals. We'll do our big brace on that left-hand side. Now the first row represents the first term, which we know in the pattern it was given. That's 12. And that means n equals 1 for our first term in the sequence. To get consecutive terms, we multiply that previous term by the R value, which for our problem now is 4/5, times A sub n minus 1 for all values of n greater than 1. There's your recursive definition. Let's throw in an application problem for fun. A phone tree is when one person calls a certain number of people, then those people call the same number of people, and so on. In the 5th round of this phone tree, 243 people were called. Write an explicit definition to find the number of people called in each round. What I'm going to do is zoom in over here to this right-hand side to look at, looks like, I don't know, a phone is being used each time. So the first person here is making the call. That means the first round, That means the first round, how many people were called total? We have 1, 2, 3. So in the first round, 3 people were called. Notice each of those 3 people call 3 people. So in the next round, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So in the next round of calls, there are a total of 9 people that were called. Then we have these 3, and these 3, 3, and 3 again. How many people were called in that third round? That would be 27. Looking at this pattern, we've got 3, 9, 27, and then I notice in the 5th round, 243 people were called. So 3, 9, 27, and then 243. That's crazy. Let's figure out if we can determine the explicit formula. The template for explicit is A sub n equals A sub 1 times R to the n minus 1 power. A sub 1 is that first term. That means 3 people were called in the first round of the phone tree. And R is how many people get called, the product of people that get called each time. It looks like we're multiplying by 3 each time. So if we figure out A sub n equals 3 times 3 to the n minus 1 power, just remember that 3 is on its own with that exponent. That would be the explicit definition. So let's go ahead and check this. Would it be true for that 5th round, A sub 5? If we plug in 5 for n on the right-hand side, five minus 1 is 4. 3 to the 4th power is 81. And 81 times 3 would be, in fact, 243. That's how many people were called in the 5th round. Based on our model in Part A, how many people would be called in the 8th round on that phone tree? If we want to determine A sub 8, we'll plug in 8 on the right-hand side. 8 minus 1 power. 8 minus 1 is 7. 3 times 3 to the 7th power would be 6,561 people that were called in that phone tree. And that's the thing with geometric. The numbers get really big really, really fast. The last thing that I'll have you do today is write down the definitions for a finite geometric series and infinite. So that'll be interesting too. If the pattern goes on forever, can you create a sum? Looking at these two definitions, we'll start with finite. S sub n equals a sub 1 times 1 minus r to the n power, all divided by 1 minus r. So remember, n is the number of terms. The a sub 1 value is the first term. But notice, unlike arithmetic, we don't technically need that last term. We just need the r value, which is the common ratio, what we multiply by each time. For an infinite geometric series, that means something that has a dot, 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 or goes on forever, you can actually create the sum or find the sum as long as your r value has an absolute value that's less than 1. So that means you could use the infinity symbol. The sum of infinitely many terms is equal to a sub 1 divided by 1 minus r. Now when we pick this up in class, we'll finish out the lesson and look at when we can find sums for geometric and when it's not possible.